Okay. Well, I'm Marv Geller, and I'm in the closing stages of being president of the Atmospheric Science section. And it's my very great pleasure always to introduce the two special lectures, the Berknes lecture at the fall meeting and the Charney lecture at the spring meeting. And today's lecturer is Dr. Thomas Peter, and I've had the good fortune of knowing Thomas for the last several years in connection with our activities on Spark. Thomas, we were very fortunate to attract Thomas from his work in plasma and atomic physics, where he was doing work on confinement fusions. You'll notice the relation to his lecture today, I'm certain. He received his PhD in physics in 1988 from Technical University in Munich. He joined the Max Planck Institute at Mainz in 1990. You might be aware that other very famous atmospheric scientists have and continue to be at Mainz. And in 1995, he has started his own research group at Mainz, focusing on microphysics and heterogeneous chemistry, sort of new chemistry, if you will, in the atmospheric sciences. In 1999, Switzerland pulled a coup, and it was a disaster for German science when Thomas left Mainz and went to work at ETH, where he continues to work at the moment. And his lecture today is it has the title, The Microphysical Control of Stratospheric Humidity and the Tropical Tropopause / Arctic Ozone Recovery Connection. I give you Thomas Peter.
Thank you very much, Marv, for this introduction. Thank you very much for coming here to this talk. I'm not sure whether my mic is switched on. Can you all hear me? That's good. So it's a great honor for me to be here at this spring meeting of AGU, and at this particular, for this particular talk here in the honor of Jules Charney. He worked on global atmospheric problems, in particular also on how the global circulation is working. I will today in my lecture try to combine aspects of global circulation on the large scale with aspects on a much smaller scale, on the micro scale. You know, when a physicist at some point in his career realizes that he's not going to do one of these great things, he becomes a microphysicist, one might say. So microphysics, the physics of cloud particles and aerosol particles, and I will say little only on heterogeneous chemistry. I should thank a number of people, and I haven't listed them all here. I should thank all the people at my own research group who helped considerably in building this talk, and at my institute, Bepin Luo, Stefan Füglistager, Daniel Knopf, Thomas Koop, Heini Wernli, Christiane Vogt, to mention a few of them, and then many more at this institute. Thanks also to the APTCO community. That is a bunch of people who performed a campaign with the Russian research aircraft Geophysica in the year 1999, and most of this data is not yet published, but is in the process of being published. And there are, in particular, thanks go to Stefan Bormann, Martin Wirth from DLR, Leo Stefanutti, Rob McKenzie, Ken Caslow, Alberto Adriani, and Piero Mazzinghi. Okay, so you see one of the participants in this talk, so to say, here in the background, a large cumulonimbus cloud, which due to convective drive goes up to a certain altitude, possibly to the tropopause, and obviously brings up a lot of water vapor, but as you all know, in the past also has been speculated on whether it could do the reverse, namely by going up, bring a lot of water vapor back down again, and actually make it drier up here than it had been before. From the tropics, where such gigantic cumulonimbus clouds develop, the air is then transported first in the Hadley circulation in the tropics, and then somehow across the tropical tropopause and with the Brewer-Dobson circulation throughout the middle atmosphere, and in particular into the winter polar region. Ideas that this entire system would work this way were first put forward by Brewer in 1949. He coined the freeze drying mechanism in the cold trap, so he hypothesized that the air, in order to make the stratosphere as dry as it was known at that time, would have to go through this very cold part here. Ice particles would form, would sediment out, and then the dry air would be transported through the stratosphere. Dobson picked up this idea 7 years later. He realized that this would fit nicely the transport of ozone from the equatorial source region here, where ozone was made, to the poles, then leading to a higher ozone column at the poles than is available at the over the equator. Now, this entire concept then kind of was almost forgotten about, or at least it was discussed controversially for the next years, because it wasn't quite clear how many cells of circulation would actually develop. And in 1978, Dunkerton picked up this again and put it onto a more solid basis by realizing that this circulation would be a Lagrangian mean meridional circulation, which neglects the eddy-driven transport, which transports air forth and back, and also horizontally, of course. Now, you saw this air, after being dried off, was transported to the polar regions, and in particular to the cold pole, to the winter pole, where we have another species, another type of clouds, ice clouds in the polar winter stratosphere. This is a picture here taken in February '93 by Terry Beschler from Kiruna in northern Sweden, showing a mother-of-pearl cloud, an ice cloud, as they are known for about 100 years now. But as you also know, they have always been thought to be meteorological curiosities, if you like. Not very nice to look at, nice colors, but one wasn't quite sure whether they would do anything. And then, as you all know, about 17 years ago, when the ozone hole was discovered, soon after that, Susan Solomon and colleagues developed ideas on how heterogeneous chemical reactions would go on particles of this sort, on ice particles, and possibly also on particles of this sort, which are not ice particles, but are of another kind. The air in this picture here is coming from the left, going to the right, and you see these relatively clear-cut ice clouds here with a relatively clear rear edge, but you also see a thin haze of particles which kind of comes out of these clouds. And there's a lot of research going on the properties of such particles and what they mean for the polar stratosphere. So the content of my talk here will be, I will give you a few basics on the microphysics and chemistry of such particles. I will talk about the hypotheses of tropical dehydration, the cold trap hypothesis, which I already mentioned, stratospheric fountain hypothesis, convective overshooting, which might lead to drying, and then about a new concept, the tropical tropopause layer, the TTL. I will then also talk about hypotheses of Arctic denitrification and show in what sense these are coupled with each other, and in what sense processes that are going on here are similar or not similar to those here. And then I will talk a little bit about possible future changes. A modern view of the mean meridional circulation, and you all know this figure, cannot get along without this figure. It's from Houghton et al.'s Review of Geophysics paper in 1995, where the following picture was drawn. Deep convection with some cumulonimbus clouds reaching the tropical tropopause is then picked up by this slow transport here, driven by the extratropical pump, and then descends again here into the so-called middle world, and eventually back into the troposphere. When I say a modern view in quotation marks, then this is because this is only 8 years old, but on the other hand, changes become visible in this concept. In particular, I mean, the authors here said some cumulonimbus clouds penetrate stratosphere. This is very true, but the two they have shown do penetrate the stratosphere. And nowadays we know that most of them do not penetrate the stratosphere, but stay relatively low, 3-4 kilometers below the tropopause, and then the air somehow must go up and go into the stratosphere. Now, a unique view of what's going on here comes from satellite data. I mean, if one wants to justify such a picture as it was just drawn, that is difficult to do with in situ data. One needs a global view. Satellite data, this is the tape recorder picture that you know from Code et al., published in JGR 1996, where various satellite instruments show an upward traveling water vapor signal, which is modulated by the tropopause temperature in the tropics, and back trajectory calculations then confirmed this interpretation. This tape recorder indeed shows that the air is going up from the tropics, then stays in a relatively confined region above the tropics, and goes up to higher altitudes before the signal starts being washed out at, say, 35 or so kilometers or higher up. So we must be interested in particles around and above the tropopause. I did mention those here, the CBs, and this one here I made not going up to the tropopause, but only up to, say, 14, 15 kilometers altitude with this turret here. Then we have to be worried about cirrus clouds and subvisible cirrus clouds, subvisible clouds, which form in this layer here in the uppermost tropical troposphere. There can be very, very thin clouds indeed, and they are so thin that I couldn't resist giving them their own name, UTTCs, ultra-thin tropical clouds. I will come to those in a moment. And then if one wonders, well, what clouds can be, instead of only in the troposphere, also reach out into the stratosphere? Then the simplest thing you can do is you can look at the lapse rate, and you see that in the tropics, temperature above the cold point tropopause starts to rise relatively quickly again. In the mid-latitudes, it kind of stays constant, and in the polar regions, it can continue to fall, in particular over the winter pole, as we know, to relatively high altitudes. So it's not astonishing that we can expect maybe a few clouds here, thick clouds possibly here, but no, we wouldn't expect clouds directly above the tropical tropopause because it's too warm. So in the mid-latitudes, there can be dilute aerosols in the tropopause region, or there can be cirrus clouds possibly penetrating the tropopause. Research on this is presently going on. In the polar regions, there can be relatively thick cirrus clouds for the lower 2-3 kilometers above the tropopause. You might also want to call those very, very low polar stratospheric clouds, if you like. And then we have the young aerosol particles, which might actually be born in the tropopause region of the tropics, transported with a mean meridional circulation through the stratosphere. When it goes too high up, they completely evaporate. Then the air comes down again over the poles, and here polar stratospheric clouds can form. And the most easy thing to visualize is actually the one that was discovered at the latest point, namely that liquid polar stratospheric clouds could form by picking up HNO3. That is easy because it doesn't require any nucleation. It doesn't require the particles to solidify. On the other hand, at times, and we know that from the picture, for example, that I showed you, mother-of-pearl clouds, solidized particles can form from these liquid clouds, or NAT clouds, nitric acid trihydrate clouds. Let me now look at these clouds here, because I will do this only now and then later in my talk, concentrate only on the tropics and on the stratospheric clouds. The clouds, the dilute aerosols in the mid-latitude tropopause region, there was a paper by Keim et al. In '96 showing that chlorine activation could happen on such dilute H2SO4, H2O droplets. Gierens et al. In an Annales Geophysicae paper in '99 analyzed about 5,000 mosaic flights, showing that in about 2% of them, above the tropopause, supersaturation of ice was larger than 100%. However, Smith et al. Recently showed, based on 63 ER2 flights, that the observations of Keim et al. Presented the only case observed by the ER2. Now, what's going on here? This and this seem to contradict each other. However, we should note that they are not immediately contradicting. Gierens says 2% of these flights could show some supersaturation with respect to ice. Smith et al. Say that 1 of 60 ER2 flights shows that. Well, and these numbers are actually quite comparable. So there could be some kind of small supersaturation above the mid-latitude tropopause. Bormann et al. And Solomon et al. In '97 went further. They said, well, if there is supersaturation and dilute aerosols, they might also form cirrus above the tropopause, near or above the tropopause, and that might actually activate chlorine. And as Solomon et al. In their JGR '97 paper showed, such an activation by these lowermost cirrus clouds in the stratosphere could explain ozone trends in the lowermost stratosphere. They could contribute, at least, substantially to such trends. Again, here, Smith et al. Say, well, supersaturation with respect to ice happens only up to 500 meters above the tropopause, if at all, based on the analyses of these ER2 flights. So if such objects here exist at all. What is not controversial at all is that in the polar region, just above the tropopause, cirrus clouds or very low polar stratospheric clouds exist. So this is accepted. Let's turn to microphysical processes. What we have here is we need to look at gas-to-particle conversion and coagulation. This will go on in the tropical tropopause region. It will go on in the middle stratosphere, polar stratosphere, when the air comes down again, descends, and the Jung aerosol reforms. And it can go on in the vicinity of clouds. We need to look at the freezing process of ice. Homogeneously, this could happen, or heterogeneously. Homogeneously, we now are on a relatively safe ground, and I'll come back to this in a moment. Heterogeneously, well, there is the, as it seems, never-ending search for ice nuclei. Meteorologists have done this, have performed this search 30 years ago, 50 years ago. The search is still on. Freezing of NAT in the polar regions, how is it happening? Homogeneously or heterogeneously on ice? We need to worry about growth and evaporation. And here, the basic thing to note is growth and evaporation, the change of radii, of particle radii by time, particle size by time, is governed by the difference of the partial pressure over the minus the vapor pressure. So this is, if you like, the supersaturation, and it refers to ice particles as well as to NAT particles. And finally, the easiest process of all these microphysical processes, the sedimentation. Stokes described that, and a rule of thumb, if you like, that's always what I have in mind, is that a 1 micrometer particle falls about 1 meter per hour, very roughly. And it scales like r squared, again, very roughly. Basically, this means the droplets, small aerosol particles, remain too small to sediment substantially, while ice or NAT particles may lead to vertical redistribution. This is the easiest of the microphysical processes. However, I think it is one that is often neglected or ignored. And I must say that the stratospheric people have learned a lot about sedimentation in the last many years, whereas when I look into the literature dealing with the tropical tropopause, this is a point that often is dealt with in a hand-waving manner. Let's turn to synoptic and mesoscale effects and go to the drying hypotheses. I mentioned in 1949, Ruhr set up the picture of the cold trap, large-scale upwelling. Then there was a paper in 1980 by Robinson. He said, well, there's a lack of thick cirrus clouds spanning the globe in the equatorial regions. So how can this picture at all be true? A year later, Newell and Gould-Stewart went further. They said the mean temperature of the tropical tropopause is too warm to explain the dryness of the stratosphere, and could there be a stratospheric fountain? This was actually the title of their paper, A Stratospheric Fountain. Newell and Gould-Stewart in the Journal of Atmospheric Sciences in '81, they showed this picture here, showing lots and lots of radiosondes, and showing this region here, the Micronesian subcontinent, where more than 90% of all measurements showed that at the 100 hectopascal level, the ice saturation ratio would be 3.5 ppm of water, which they thought is appropriate for the stratosphere. There's new development in this, and I mentioned that before. We now understand homogeneous freezing of ice from solution droplets much better than we did 20 years ago. We understand in particular that such a freezing process depends only on the relative humidity over ice. However, it requires a 4K of supercooling. This is work by Cope et al., published in Nature in the year 2000, which unifies freezing nucleation temperatures and rates for 18 different aqueous solutions. These were the solutions that these authors looked at, and on the left plot you see the melting temperatures of these various solutions and the freezing temperatures in red of these solutions as a function of concentration of these solutions. When transferring this picture to a water activity-based diagram, so instead of molality, water activity, and water activity is nothing else but relative humidity over ice, then all these curves here collapse to 1. This is not astonishing. This is thermodynamics. However, what is astonishing is that also these kinetic curves here, the nucleation curves, formation of ice, they also collapse to 1 line. The reason for this is that it is water activity which defines the structure of the water in these supercooled solutions. And therefore, when plotting these data as a function of water activity, this all comes down to 1 line. So I'm saying here quantitative thermodynamic ice freezing theory, and I usually don't use the word theory that easily, but here I would really say it's a major breakthrough. So if we can be sure that in the atmosphere, under certain circumstances, heterogeneous nucleation is not happening, then this description of homogeneous ice freezing is perfect. We think we can say we understand this now very well. For example, it can be used to model cirrus cloud formation based on homogeneous nucleation of ice. This is a figure from a paper by Jensen et al., published in JGR 2001. Here you see how the relative humidity as a function of time in days, over 10 days here, is slowly increasing because the air is rising up. And he modeled how then a cirrus cloud would come about. And you see there are nucleation events now happening of ice based on homogeneous nucleation. So there's a first event, a second event, so it goes a bit up and down, but essentially a big cloud is formed and the particles also start to sediment. And because the supercooling is required of 4K, this means that in the vicinity where the cloud onset is, there is a large region supercooled. In other words, the particles now have a free fall in a supersaturated environment, And this necessarily means that homogeneous nucleation of ice will always cause cirrus clouds which are at least 2 kilometers thick. This is an important finding, because we will see later that we know of many clouds which are much thinner than 2 kilometers. So, however, as I said, this kind of freezing mechanism requires 4K of supercooling. And if we apply this to the mountain, to the fountain region, then this region shrinks to tiny patches, because now we are not allowed to simply say, well, ice saturation at this altitude. What we need to go to ice saturation minus 4K, quite a bit colder. So let's take this away and look at the second process, the convective overshooting. That was formulated by Danielson in a GRL in '92, irreversible overshooting of cumulonimbus cirrus clouds, that is this part here. And then he also described a drying process in the convectively overturning anvils over here, that is this second, number 2. I cannot resist on showing a few nice pictures here. You go to the NASA websites and you find this. You see these cirrus clouds in the tropics and these anvils with their turrets. However, the basic question for us is, do these towering clouds lead to hydration or to dehydration of the UTLS? And it was already Danielson who did not try to make a curve around the possibility that these clouds were actually hydrating and not dehydrating, because the first thing they are doing is get up a lot of water. So his picture is sketched here. He was, I mean, in a very simple approximation, you could think about an air parcel rising moist adiabatically. Its temperature remains, due to the release of latent heat, above the ambient temperature. Therefore, it continues to accelerate to this equilibrium level, and then it overshoots into the stratosphere and then falls down again, because it has used up its energy basically already here, but because of its kinetic energy, it continues to go up. That's converted into potential energy and then falls down again. He realized that, of course, what would be happening is, if this air up here decides to fall down again, there is further air coming from low down, and the two will collide. Due to this and the entrainment of air in this uppermost part of this upwelling motion, the air will not continue to follow the temperature with no entrainment, but rather go to a point here and then adiabatically descend, end up at a temperature much colder than if it had come down again to the equilibrium level. So there is this overshooting with very low temperatures, and ice crystals will definitely form in this or be in this overshooting dirt. The question is, are they big enough to fall down? And then there is this radiatively driven anvil convection here. The anvil is heated from below, from the long wave radiation from the ground, and cooled above, radiating off to space. This leads to this sigma-shaped temperature profile that was also measured. And the question remains, will the ice crystals become large enough to actually fall out? We now turn to the third process, a mesoscale process. Waves can lead to dehydration in the tropopause region. There's a bunch of paper talking about convectively driven meso-highs. Then in '95, Potter and Holton described gravity waves-induced ice forming in the tropical lower stratosphere. This is remarkable. Böhm and Verlinde, a paper in 2000 showing Kelvin waves driving the formation of upper tropospheric cirrus clouds. A plot of this nice paper is shown here, where you see how this wave comes in cold and warm phases, changing the altitude of the tropopause, and each time in a cold phase, not each time, but mostly in a cold phase, you get the formation of these cirrus clouds. That's these black symbols down here. Fujiwara et al. In a GRL last year called Kelvin Waves a dehydration pump actually working here at the tropical tropopause. And then there's presently appearing, I think, Holger Firmel's JGR giving further indication for such a process, but also giving, based on a rich data set gathered over the last years, information on cirrus formation and on the dehydration by deep convection. The last point in the synoptic and mesoscale effects section here is on the tropical tropopause layer. There was a paper 3 years ago by Folkins et al. Introducing the tropical tropopause layer as a vertical mixing barrier at 14 kilometers altitude. This is marked here by the difference between where the ozone starts to increase again and where actually the cold point tropopause is. So the idea is that the air from this level upward is left alone, so to say, and has a long time to build up ozone and to stay within this layer. The tropical tropopause layer can further be characterized by the lack of high or very high convection. This shows here the cumulative distribution of storm height obtained from the TRIM data set, cloud height as a function of cloud height, and you see here that up to the 14-kilometer level, about 30% of all deep convective events go, whereas up to the tropopause, only a vanishingly small percentage. We tried to model that, and what I show you here is a model, a few thousands trajectories, backward trajectories or forward trajectories based on ECMWF data released at the 360 Kelvin level in the tropics. So it's this picture here, and I'll now show you this movie. It will start in a second, I hope. So this is after 2 days, and each frame here you see here is another 2 days, and you see how it develops. And here on the left side you see which parcel actually left this 30 degrees south to 30 north region. And that goes over 60 days, and you see that at the end of these 60 days, most of the air parcels are still there. So this layer seems to be quite confined. Okay, I come to the consequences of this tropical tropopause layer. Sherwood and Dessler discussed in the year 2001 a dehydration mechanism. Dehydration in deep convection going up into the tropical tropopause layer, releasing very dry air here, which is then mixed within this layer. So the idea is like this, while the conventional view thinks that the deep convection goes up to some layer, releases the air, and then the air has to go up slowly, and there will be further dehydration. This hatched region here is the dehydration due to the formation of cirrus clouds. In this picture here, the air is all dehydrated in this convective overshoot, and then this releases the dry air, which is then initially drier than the average in this layer and will be mixed into this layer. Okay, so the last point to describe here are the dehydration hypotheses of the polar stratospheric clouds. And there is currently a battle about whether these form homogeneously. This is a paper by Tapazadeh et al., which appeared a year ago in Science, or heterogeneous nucleation of NAT on mother-of-pearl clouds. There are papers by Daniala et al. From Paul Wenberg's group and Füglistaller et al. Appearing in GRL presently. Concerning polar observations, there are two major breakthroughs from the SOLVE campaign. The first one is observations of very large HNO3 containing particles, a paper by Fay et al. In Science, who observed I call them NAT rocks. Sorry, it's slang, so to say, but it's a nice, catchy word. They are really very large, haven't been observed going up to more than 10 micrometers, and on the average 7 micrometers in radius. Very low density, only 10 to the minus 4 particles per cubic centimeter. You see here, as a function of time, the measurements of the David Faye's NOI instrument, showing individual peaks which all refer to one individual NAT particle or several in the dense parts of the cloud going into the instrument and picked up individually. Then there is a second thing from Konrad Rauersberger's group appeared a paper by Vogt et al. In Science 2001. They measured with a balloon-borne mass spectrometer NAT particles. So they analyzed the molar ratio of HNO3 to water in the particles. And for the first time, I mean, it was also Mauersberger in '96 with David Hansen, who described the NAT vapor pressure for the first time. And it took, obviously, many, many years, almost 15 years, to actually prove that these particles are in the stratosphere with a direct measurement. Okay. Both tropical dehydration and polar denitrification are determined by the same two critical issues. First, we have to ask the question, how do temperatures get low enough for long enough times for the particles to fully empty the gas phase? And second, how do particles get large enough to develop efficient sedimentation, that is to fall out before the air warms again? This just lost its capabilities, but I think I can do without. A few back-on-the-envelope remarks. The final particle radius can be estimated from knowing what the mixing ratio in the condensed phase is divided by the number of particles per cubic centimeter, and taking the third root of this. This is very simple. Growth and evaporation, I mentioned this growth law in the beginning, and when you integrate that, you find that the time for doubling the size of the particle goes with a radius squared over the condensed phase mixing ratio. And finally, the sedimentation Stokes law. A few examples. First example, let's assume vigorous updraft, transporting from the boundary layer air which is completely humidified, 5% of water in the air, up immediately to the tropopause. And let's assume 100 particles per cubic centimeter would form, because this rapid upwelling, of course, will nucleate a lot of particles. Then these particles will be 20 microns in radius. It will take them very, very short time to grow to this radius. And their sedimentation velocity will be about 400 meters per hour. So we better give them about an hour in this turret to empty a 400-meter layer, make it free of water, so to say. Second example, we could imagine mild updraft in a high zero stack. Only 10 ppm of water can condense because there isn't more available. And let's say only 10 particles per liter would form. Then, interestingly enough, these particles again are around 20 to 25 microns in radius. They have the same sedimentation velocity. It takes them a bit longer to grow because vapor pressures, and therefore the growth drive is slower, but again, only a matter of minutes. And finally, the formation of large net particles in the polar stratosphere. There we only have 10 ppb of condensable material, of HNO3. We have observed that there are typically 10 to the minus 4 particles per cubic centimeter. They are somewhat smaller, but not really dramatically smaller. They reach 10 microns in radius, a sedimentation velocity of 100 meters. And, but it takes them 5 days to grow because of these low vapor pressures. Let's test these convection mechanisms. And I should look at, Jesus, I'm running out of time. Let's first look at the deep convection mechanism. There was the STEP tropical campaign in Darwin in '87, and the paper by Knollenberg, Kelly, and Wilson nicely summarizes the findings. The particles in the anvil have the properties that there are indeed many of them, surprisingly many, 10 to 100 per cubic centimeter, due to this rapid upwelling. They said homogeneous nucleation is required to explain so many particles. and this is not astonishing in this rapid upwelling. 10 to 20 microns in radius, a nice water content, which is huge. It's 0.1 gram per cubic centimeter or 1,000 ppm. And I think it's fair to say that overall this entire campaign remained, I would say, inconclusive concerning whether there's hydration or dehydration. The problem is, as I view it, that you are bringing up a megaton of water in such a storm in order to now get this entire megaton back down again, and in addition, the 1 kiloton of water that was in that huge region up there before. That's maybe a problem. Further testing the deep convection mechanism. In their paper in 2001, Sherwood and Dessler put forward evidence for the existence of this upwelling into the TTL, drying, and then the mixing into the layer. If this really happened, then in the layer, in this TTL, one would expect that young air parcels with relatively low ozone mixing ratios, and so these are parcels over here, and old parcels with relatively high ozone mixing ratios would be correlated with water. Looking at the overall ozone-water correlation, that goes the other way around, of course. Either you have stratospheric air, which is rich in ozone, low in water, or you have tropospheric air, which is the other way around. So here we have a correlation like this. Here we have a correlation the other way around. How can that be? And the point is that if you look at slices of potential temperature, which are very thin, say 380 K plus minus 5 K, then one could expect really to see this aging effect. And this is on 4 flights here, ER2 flights, which they illustrate. So they see kind of a positive correlation between ozone and water. We have looked at the same thing from the 7 flights of the Geophysica in February '99 over the Seychelles. These data here. Different colors indicate different flights. And as you see, we do not see anything of that sort. As a matter of fact, similarly small slices in potential temperature, and they fill the spectrum indeed like this, not like that. So it could be that the flights that Sherwood and Dessler looked at were actually influenced by deep convection, while we have a lot of evidence that in this campaign on the Seychelles, there was not much deep convection. So let's look at this campaign a little bit closer. It means testing the cold trap hypothesis. It's the Arpetiseo campaign, which took place using the combination of the Russian Geophysica and the German Falcon. The 2 aircraft have the nice property that they can fly with the same speed, one at 12 or 14 to 14 kilometers altitude, the other one at 20. So you see the contrail of the Geophysica up here. On that day, we were on our way from the Seychelles, which are here at 55 east, 5 south, to a tropical storm, which was almost 1,000 kilometers away. Let's focus onto this a little bit closer. The flight path that we flew was like this. We came from the Seychelles. The pilot had the task to approach the storm from above and go in each of these forth and back maneuvers a bit lower towards the storm, and then we returned back home. And these red stripes here are where these ultra-thin tropical tropopause clouds had been observed. We didn't expect to see them, but when we came back home, we did see them. This is the 1064 nanometer backscatter seen from the Falcon flying at 12 or 11 kilometers altitude. Thin cirrus lower down, and here they also are visible in the 532 nanometer backscatter ratio. Now this was the one that we looked at during the flight, and here we truly did not see this thin object here. And this is what we ultra-thin tropical tropopause cloud is. We see that also in the FSSP 300 measurements on board of the geophysicar. In black here you see number densities of particles throughout this entire flight. You see with this line the altitude of the aircraft. And in blue you see the volume density observed. So the interpretation of this time series is as follows. This reddish region here shows the deep convective cell and the anvil, and each time the aircraft penetrates this cloud, you see how the volume of particles shoots up. However, there are a few instances, namely here and here and here. Each time the aircraft is much higher up, which cannot be explained by these lower clouds, but can be explained by a very thin cloud up here, the UTTC. This is shown again in this plot here. Here you see the geophysicar maneuvering through this thin cloud. When the pilot is flying horizontally within this cloud, he doesn't see it. So he has to be maneuvered by the aircraft below. And this is the number density measured by the FSSP. So you see typically these particles have 5 microns in radius. This is an overall picture of this flight showing the LiDAR, the aerosol LiDAR measurements. This was our goal, the deep convective cell back here, which reached an overall altitude in its turrets of 14 kilometers. And then we found that the interesting stuff was lying much closer to home than what we were heading at. It's these thin layers here. Sometimes we have a double tropopause, so we see 2 of these layers. They are very close to the tropopause, as I'll explain in a second. So 3 days later, we said, now we aim at measuring these clouds. And, sorry, that was a bit too fast. And here you see the flight path of the geophysicar through these clouds. And we will now look at a zoom of this part back here. This is shown here. Here you see a 400-kilometer long detail of this entire flight, and you see how the pilot is maneuvering up and down as he was told by the Falcon looking from below. And you see each time when the aircraft penetrates this thin cloud here, the in situ backscatter instruments go up. You also see that the depolarization goes up, so these particles are not spherical, they must be crystals. And you see how the water vapor measurement also goes up each time. This is the fish on board of the Jülich instrument on board of the geophysicar. What you also see is that HNO3, which was measured in the particles, is not showing a signal. So there's no indication of HNO3 in these tropical particles. Similarly, thin clouds have been measured before. There's this beautiful paper here by Dave Winker and Chip Clapter in GRL 98 showing from the light measurements, showing deep convective systems here in the tropics, and then a very, very thin and very long cloud. I think it's not ultra thin, because if we try to estimate what the optical density here is, that is still about a factor of 10 higher than the ultra thin clouds. But you see the massive extent of these clouds. They put this into a climatology where they distinguish deep convection from thin clouds, and you see how it spans the entire tropics. I move a bit faster, skip this one. There is a JGR in 2001 by Omar and Gardner, and based on the light data, they conclude that a significant number of these high altitude clouds in this range have optical similarities to type 1a polar stratospheric clouds, net particles. 66% of them are very thin with such a backscattering ratio. Now, you saw that we did not see these ultra-thin clouds at 532 nanometers at all. They were invisible there. We had to look at 1064 nanometers, and there are at 532 would correspond to something much lower than 1.1. Since these clouds are most likely form at these low temperatures, it must be considered that size and composition are similar to polar stratospheric clouds. There is a thin cirrus climatology, McFarquhar and Hamesfield and Hart published only a few years ago these older measurements here showing ER2 measurements and showing a distribution over optical density of thin clouds in the tropics. And when I compare this with our measurements, we found these ultra-thin clouds to appear over 31% of all the time. This is this year. You see that this distribution looks quite different from what was found before. So we think that these ultra-thin clouds are there quite often. And it's just very, very hard to see them. So we can summarize to this point. They are the thinnest subvisible clouds observed, I think. They show a large extent, a high occurrence frequency, 30% of all the time. The composition is probably not NAT, because we had low particulate HNO3, and there are other investigations which show that they can't be NAT. They are probably water ice, because also the water instrument was going up quite a bit when the aircraft flew through these clouds. What is their relevance for dehydration? They are 5 microns in radius, typically. They are very, very thin, only 4 to 10 particles per liter. They have an optical density of 1 to 5 times 10 to the minus 4, very, very thin. And their mixing ratio of the condensed phase is 20 to 50 ppb, provided they do consist of water. And here's the paradox, and that kept us from not even trying to publish these data for a long time because we really didn't understand them. And the paradox is, how easy is it to condense 20 to 40 ppb of water as ice when a total of 2 to 4 ppm in the gas phase is available? And usually I hesitate at this a little bit and ask the audience, so can you give me an answer? How easy is it to condense about 1% of water? Imagine you have a box and you go in the laboratory, take a box, you want to condense 1% of the water in that box as ice. Is that easy? Is it easy? No, of course it is not easy. It's quite difficult, right? And the reason for that is that one must stay awfully close to the frost point. You go up 0.1 K, and that cloud will be gone because it's too warm. You go down 0.1 K, and the signal will be inconsistent with what was observed by the LiDAR, what was measured by the FSSP, and so on. Another problem, what keeps them aloft? Their sedimentation speed, because they are 5 microns in radius, is 5 millimeters per second. It's a relatively large speed. So a comparable updraft must be there. The Brewer-Dobson circulation, on the other hand, is an order of magnitude slower. The Hadley circulation is slower. Deep convection could do it. Well, there everything is possible. We need a stabilization mechanism. Let's have a quick excursion to the Arctic. Could UTTCs consist of NAT? Well, the reason for that sensitivity to the temperature is that the Clausius-Clapeyron equation gives us such a steep dependence here. If they consisted of NAT, we would have a few degrees available. Temperature could go up and down. It wouldn't harm that cloud. There are currently a few potential pathways discussed for NAT nucleation. There's homogeneous freezing nucleation discussed by Tabata et al. Heterogeneous was once mentioned. Well, we really have a bad understanding of what heterogeneous nuclei are doing, no matter where. It's difficult to study them. And third, deposition nucleation on ice particles. There are many buts. This one here, basically already in a paper from 1995, one would say freezing rates are much too low to explain homogeneous freezing nucleation in ternary solution droplets. The second one here, no suitable nuclei have been found. In a laboratory experiment, one put a lot of stuff into such solutions, cooled them to stratospheric temperatures. They still didn't freeze. And this third one here, deposition nucleation on ice particles, well, if these cloud fields of NAT rocks observed by David Ferry would actually depend on mother-of-pearl clouds, which are very patchy, wouldn't one also expect these nat rock feels to be patchy. So that was the criticism at this hypothesis here. The proposal of nat, I must honestly say, I still don't believe. Tabatarzadeh et al. In their paper showed nucleation production rates of NAD and NAD, the dihydrate of nitric acid, of this kind, and this was based on the parameterization of nucleation measurements performed in the laboratory by Salcedo et al. In 2001. This parameterization, however, is a parameterization of the nucleation rate, which is based on these measurements shown by these black dots here, whereas the stratosphere is over here. So we must extrapolate this long way, and this is what was done by Tabatarzadeh et al. And this extrapolation is really questionable. It's questionable because if you take this parameterization as is, you see that it doesn't go to zero nucleation rate at the boundary of the NAD existence regime, as it should, because when the liquid and NAD are in equilibrium, no nucleation should happen anymore. And there are new measurements which are currently published, which show that in the laboratory, going actually to these regions here and doing measurements there, that these nucleation rates were probably much too high. There's another mechanism. Ice particle formation does happen. We see them every year in the Arctic, maybe not in the warmest winters, but every other year. And the air, when it goes over the mountains, the Scandinavian mountains, of course, for example, goes up and down and can be cooled adiabatically and actually go down to this low temperature. Particles pick up HNO3, form ice at the force point -4. On the ice, NAD can deposit. The ice evaporates again, but the NAD survives. So we know that such mountains can be the source of dense NAD clouds. The only crucial question is, are these dense NAD clouds suited at their lower edge to let NAD particles sediment out? And this is indeed what is proposed. Large NAD particle formation on mother cloud. On mother clouds, so it's the mother cloud NAD rock mechanism. This red region up here is the mother cloud. This shows number density, and here 10 to the -1 NAD particles per cubic centimeter. And this is a model that we performed over 120 hours as a function of altitude, showing the development of this initially confined NAD particle ensemble, how slowly the particles sediment out. They fall into supersaturated air below here, therefore they fall and at the same time grow, and hence they fall quicker and quicker. And the dimensions of the atmosphere are such that no matter with what density you start out with up here, you always end up with 10 to the -4 to 10 to the -3 particles, NAD particles per cubic centimeter lower down. We have looked at this in a backward trajectory analysis. There was this massive SOLVE campaign, but it's astonishing. Still, the number of matches where we can say, aha, here we looked at one air parcel, measured the particles in that air parcel. 3 days later, we look again at that same air parcel and look at what the particles have done at that time. The number of such matches is exceedingly rare. I think it's 1. And this 1 is shown here. And this one is a double one. That's good about it. So the particles were first observed over New Orleans by the LiDAR there on the 26th of January, and then they were seen over here by the ER2 by the DCA 3 days later, and then another 2 days later by the ER2 here. So we have measurements, and we can compare these particle trajectories here with the measurements. This is now what these measurements, what the simulation looks like under these realistic conditions, while this was a simplified version up there. And this is what is measured, for example, here on day 29 by the DC8, seeing this cloud, and this is the modeling. So this seems to fit, and there's another group, Paul Wenberg's group, which have developed these ideas. I'm close to my end, right? That's a problem because I should get to the future, I suppose. Let's see. I skip a few things here. This explains the UTTC paradox. It's a stabilization mechanism. These UTTCs form out of, we think, out of high, thicker cirrus clouds. When they evaporate due to warming, a supersaturation remains above the cloud and subsaturation below the cloud, and this is a point of stability. Whenever a particle that is sitting at this spot falls down, it gets into subsaturated regions, gets smaller, is driven back again by the upwelling motion to this level of stability. This also explains why it is so thin, and I now should, Mark, do I have another 3 minutes? Great. Have a brief look into the future. How will the tropopause region and hence the stratosphere develop? All these things I talked about, I touched on, are connected with each other. Cloud development, temperatures, water vapor. As you know, there are, one could say interesting, or one could say worrying observations showing that water vapor is increasing. There is a trend of about 1% per year in the in the global stratosphere, basically, of water vapor. In a paper in 1999, Evans et al. Show that this trend is global and at all stratospheric levels, that CH4 oxidation can account only for half of this trend. There's a volcanic and solar influences can be excluded. So it could be an increase in the tropopause injection temperature. However, in a paper in JGR 2001, Seidel et al. Show that there is actually no trend at the tropical tropopause in temperature, or if there is one, then it's slightly negative. So it's getting colder. What does that mean? That means that if we cannot explain this trend by CH4, if we cannot explain it by temperatures at the tropical tropopause, it could be, and this was put forward by Steve Sherwood in his science paper 2002, by a change in the particle properties by themselves. And what he shows is that at two different potential temperatures, the relative humidity is very much in phase, observed by Halo over a number of years. And then he compares that with ISKIP data for the effective radius of these particles, which he plots downwards, also being very much in phase. And concludes from that that the effective radius is controlling the relative humidity over ice. There's a semi-annual variation of that effective radius, which is in phase with a semi-annual variation in biomass burning. So it could be that more particles get up there. That makes the ice particles smaller and therefore more capable of going into the stratosphere and passing through the tropopause. The water increase in the stratosphere could lead to additional stratospheric cooling, and this cooling, as shown here, could in particular affect the polar regions, and the observed temperature changes over the last many years, based on the Berlin data, do indeed show also in the Arctic a cooling of, say, half a K per decade. If you now continued this for the next many years, the Arctic would become more and more Antarctic-like. That would mean that denitrification, as has been observed in the Fahey data, could become more and more common in the future years, which again could mean that polar ozone loss, despite the fact that chlorine is slowly going down, could be enhanced in the next 1 or 2 decades. So I wanted to show you more on that. Obviously had too much fun early on, and it was put like this by Pat McCormick yesterday. I thought that's a nice summary of my own behavior here. Thank you very much for being so patient and being with me to this point.
Thank you very much. That was a fascinating talk, and that's why I didn't get up sooner. It was, everything was very good. We could probably take maybe 1 or 2 questions, if there are any from the audience. Yes?
And we talked a lot about the possibility of being nitric acid concentrated. Have you thought about the incorporation of sulfuric acid particles in the freezing of the octahydrate?
The octahydrate I haven't thought about, or actually I should say we have looked in a Paul trap, suspending a little particle for the octahydrate and didn't find any evidence for the octahydrate. All I can say is that from the laboratory experiments, always when you have sulfuric acid there, in addition to water and nitric acid, this sulfuric acid seems to suppress quite efficiently any kind of nucleation of nitric acid hydrates. So that's a general observation. And as nature usually does have that sulfuric acid with it, and laboratory experiments quite often are ignoring it, this is a problem indeed.
Any other quick question? Liz? Sure.
I just wanted to make a comment. You were saying that the water colors and plastic acid and showing that treatment with positives and water colors. And I just wanted to say that usually in the ICU investigation in summer 2001, and we see the exact same thing with that, we see the normal expected stratospheric areas rather than
Right. Okay. So I was careful in saying that maybe the Seychelles campaign was without deep convection, while the ER2 flights analyzed by Dessler and Sherwood were deeply convective. But now you are saying that even in deep convection, you have a difficulty finding such a positive water-ozone relationship. All right. All right.
Do you want a quick comment on that, Andy?
Yes. We took the same filter as you, the N2O filter with the same function you used.
Okay, I'm sorry. This is fascinating, and I'm sure we can corner Thomas. I should just close by saying that I think Jules Charney would have enjoyed this talk very, very much, and as I did. Thank you.
Thank you very much.